Well, thank you very much, Didier, for the introduction, and thank you to everybody for joining in such large numbers, for the interest in Odyssee-Mure, of course, as a project, which I think is quite unique, and in particular in this topic of retrofitting the building stock. This is work which I have supervised in the context of a PhD project conducted by Kai Nino Streicher. Kai defended his thesis very successfully in December 2020, so a little bit more than a year ago. All the material is available publicly. It was a cumulative PhD thesis, so there are individual papers, and at the very end of my presentation, you will see the most important ones, as well as the link to the entire PhD thesis. As a quick background, since the starting point is energy efficiency first, here comes a definition. Probably there are several, but here comes one by the European Commission from 2018, which refers to energy efficiency first as a strategy which takes utmost account in energy planning and policy and decisions of cost-effective, that's important, obviously, cost-effective measures. And what is stressed here is actually the first one which is mentioned is end-use energy savings. So cost-effective end-use energy savings. Mind you, all the others are also mentioned. So maybe the first refers to the fact that it's mentioned first here. But I'll come back to this definition later, because the question is how we identify these types of measures and how we indeed assess them. That I'd like to refer to the situation in Switzerland, give you some background of the Swiss energy strategy. As you know, Switzerland is one of the countries which decided to phase out nuclear energy. Also Belgium, Germany, Spain, Sweden decided not to build any new nuclear power plants and to phase out the existing ones. So that means for Switzerland, that means that everything which is currently nuclear is supposed to become renewable. So far, Swiss electricity has been practically zero carbon, because apart from nuclear, which is maybe around 40% decreasing, actually, because already one power plant was shut down, the rest is hydro, essentially, so hardly any thermal power plants. Now, of course, there is a question whether it will remain net zero, because supply security is a concern, as in the EU, also in Switzerland. And that is complicated by the fact that Switzerland withdrew from the framework agreement. So this is important, I'm mentioning it, because when we talk about decarbonization of space heating, the electricity should actually be zero carbon. There is also an objective of reducing final energy demand in Switzerland by about 1/3 from 2020 until 2050. It has been extended the range until 2060 recently. And these reduction objectives are actually not super ambitious compared to what it was before. So there was a study, this is actually a brand new study, which was just released in December by the so-called Energy Perspectives Group, which is under the leadership of the Swiss Federal Office of Energy. So this is the title. And originally, until since 2014 and until the publication of this new perspectives, we had a reduction of final energy demand as an objective of nearly 50%, 46%. So the focus has been actually now in the new version, in the new edition, more on the reduction of CO2 emissions, on decarbonization, at the cost to some extent of energy efficiency. So the objective is, as you see here, 1 ton per capita and year, which is without CCS, without negative emission technologies, which is very good and which implies a reduction by 80%. So already the starting point is not very high in Switzerland because of the basically CO2-free electricity, but also because there's no CO2 intensive, energy intensive industry. Then we move to households. Actually, I've been saying I'll be talking about the building stock, but the focus will be on the residential building stock. And there the objective from 2020 to 2050 is 18%, so even less than this 1/3, which means that other sectors have to reduce their energy demand more in this time period. So nearly 20% reduction of total final energy demand, but clearly more per capita. This has to do with the fact that Switzerland, in terms of inhabitants, is still growing. If we look at studies which have been done in the last 3 years, so before the release of these new energy perspectives, then we see that they aim for a very, very strong reduction, not only of energy use, kilowatt hours per square meter and year, but also of the CO2 emissions per square meter and year. So in parallel, energy efficiency improvement and decarbonization with somewhat different slopes. And due to the new strategy, the new focus, I would expect that the slope will actually become more steep. So yeah, more quick CO2 emissions relative to the energy intensity reduction. So this is just a quick background before we now proceed with the methodology. The methodology which Kai Streicher developed is based on archetypes. So this is a data-driven approach where he distinguishes different categories of the Swiss residential building stock by distinguishing 9 different age categories, 2 types of buildings, multifamily houses, single-family houses, different urban settings, and different fuel types. So in total, already 324 archetypes. He then uses actually a big data approach because he uses the energy efficiency certificates. So he can do a statistical analysis on this and come up with representative archetypes for each of these 324. In addition, he accounts for the location, so it's linked to a GIS model where he considers that the weather is different in every place. So we do have the required data from the building inventory, and that allows in total then to reproduce the energy demand for these various categories. So here you just see the age type, the different types of buildings, and the urban settings, and then the specific energy demand. So the final energy demand in kilowatt hours per square meter and year, which if they're then multiplied with the floor area lead, so energy reference area, lead to the total energy demand here expressed in percent. So you can identify the hotspots where the energy demand is high, both in specific terms, so in kilowatt hours per square meter and year, but also in absolute terms. So that would be, let's say, in terajoules. Now, this was just the starting point, and I will show some results based on this because this already leads to quite interesting results. But what I would focus on, as you know, like to focus on is the retrofit options, where Kai, we were collaborating with an association which is called Minergie, so minimal energy, which is an association offering labels and also technical solution packages. So far, they have been focusing primarily on new buildings, and more recently, they're looking into energy retrofit. So there are 6 systems, 6 retrofit solutions, which they have developed also with the HSLU, which is the University of Applied Science in Lucerne. And we will quickly go through them because I'll refer to them back in one of the slides later on. So as you see, system one would imply a very, very good insulation of the building envelope, comparable to the system P, so that's passive house level. But it would still be using, system one would still be using a fossil fuel boiler. Then system 2 to 4, they have a partial energy retrofit, but they do have a heat pump. Of particular interest could be system 5, because there the idea is not to modify the facade. So that could be necessary if you have protected buildings. And finally, as I already mentioned, system P, which is the passive house building, and which combines a very, very good thermal performance of the envelope with a heat pump. In addition, these buildings also have mechanical, and they have a mechanical ventilation to ensure heat recovery. This would apply to system 2 until system P. Why? Because, I'm sorry, it would only apply to system 1 and to system P. Why? Because this is a very heavy retrofit which would be required in order to make that possible, that heat recovery. Okay, so just in a nutshell, only system 1 has fossil, all the others have heat pumps, and system P sticks out in terms of thermal performance together with system 1. The way we studied the various options which we have are these energy efficiency cost curves. I guess most of you are familiar with them, but I will nevertheless very briefly introduce it as a concept. So the idea is to plot the energy saving potential relative to the cost of individual energy efficiency measures. So we are doing this with discounting. So this is a levelized cost approach. So on the y-axis, you see the specific cost, levelized cost for saving 1 unit of final energy, 1 megawatt hour in this case. And this entire section here would be, for example, 1 measure. Let's say these are windows. I don't really know what exactly it is, but it could be anything. Let's say replacing the windows. So on the x-axis, you would have the expected savings. By doing so, you see that some others have lower values on the y-axis, which means that they have lower cost. And then we have on the x-axis, we have on the y-axis we have the cost, and on the x-axis we have the expected savings. Now, what is particular here, as you see, the costs are negative. So these are win-win solutions. These are solutions down here which are cost effective, whereas as soon as we cross the x-axis, we come into the space where we have a net cost for the measures. All right, so the lower we are below the x-axis, the better. And the more we go to the right, the more savings we accumulate by adding up these individual measures. So since indeed we are crossing here the x-axis, the total of the curve, which is actually below or until 0, so where it crosses the x-axis, is the economic potential, the economic energy saving potential, economically viable potential. Now, this part about the cost assessment methods is, in first instance, I think simple, but I'll spend some time on it because I always felt also in the way we have been presenting it in the thesis and the papers, sometimes it didn't come across as I wanted to. What you see here is the first approach, which we call full cost approach, which means that we take the total cost. So here, if we have an energy retrofit, the total cost of the project is taken into account. The energy savings are calculated by taking the energy demand before minus afterwards. And the mindset here is that basically the energy savings should kind of pay off this entire investment. So this is a more profitability-oriented approach. The idea is that indeed the project kind of pays itself, which is very, very demanding, as we can imagine. And maybe not fully fair, because if we insulate a facade, for example, then at the end of the project, the facade will look beautiful again, whereas it was ugly beforehand. So we have a value added beyond the thermal performance improvement. And nevertheless, we would take the total cost. So instead of that, to come up with, you may say, a fairer, a more adequate assessment method, we have this improvement method, which, as you can guess, takes the total cost but deducts the anyway costs. So the costs which would have been required for refurbishing, for maybe replacing parts of the building which are damaged or have reached the end of the lifetime. And by analogy, we would then compare the energy use of the standard approach compared to the situation after retrofit. So the whole idea here is indeed to not take the total cost, but to deduct the cost which we would anyway have had. However, here the mindset is that we actually wait until the end of lifetime has been reached. So we are tuning our retrofits to basically the reinvestment cycles. And this is a good idea, of course, because we don't want to throw away something which has value, but it may actually take too long. It may be impractical. It may take too long in view of the decarbonization objectives. So in order to cater for that, we said, well, these two approaches are kind of extreme, to take either the total cost or to take only the additional cost. Maybe we should do something which is in between, which we called intrinsic value approach, or rather in the thesis we called it differently, depreciation approach, but we call it intrinsic value in this presentation because it kind of gives a value to the building itself, even at the end of the lifetime. So at the end of the lifetime, the building, as a default, would still have 20% of its original value. That means also that if we do retrofit at the end, if we even more so, if we do early retrofit, we are actually, in a way, destroying some capital. And we did that also because usually the buildings, I mean, at the end of the lifetime, of course, you could still use them. I mean, they're not useless. And people also don't like giving them up. So they also even have something which is beyond the pure physical value. They have some emotional value, let's say. So for that reason, we have been doing this. And then for the energy use, it becomes a bit more complicated because you have two time periods in which you have to differentiate in order to calculate the savings. I'll not go into detail of that. You can look up the papers for that. But the most important thing is indeed that we have this kind of residual value. Sometimes we call it salvage value. So the full cost of retrofit, the cost of retrofit would be the improvement cost. So that would be what we said before, the full cost minus the anyway cost. But in addition, also this residual value of the building at the moment when we do the retrofitting. So this is the approach we took. And essentially, it's represented here once more. And I'll not go through the entire graph again, but just through this left part. So here we're talking about investment. For the full approach, we take the entire energy retrofit cost. For the improvement approach, we take that total cost, but we deduct these refurbishment costs, which we would anyway have had. And in the intrinsic approach, we take the result of the improvement approach, but we add the residual value of the building at the time of retrofitting. And the approaches we would have for calculating the energy savings as well as the energy cost savings are given here. I'll not go into them. All right. So I hope this is kind of clear. We didn't find in the literature before anybody doing this intrinsic approach. I will abbreviate this as INT, whereas the others are full and INP. Okay, so this is quite important for the results later on. So here come the results, but before going into this rather complicated cost assessment, let me first show you results from the energy model for Switzerland. So you see here on the left-hand side, the specific energy demand and the specific emissions, so kilowatt hours or kilogram CO2 per square meter and year. You see areas where the specific energy demand is rather high. That has to do with two things, energy efficiency, but also with the climate. So in Jura, the buildings are relatively old, relatively inefficient, but it's also colder than in Geneva, explaining why we have much more red up here. Then if we multiply with the floor area, we arrive at the total energy demand. And you see that, for example, Geneva, which is relatively efficient compared to at least Jura, becomes more red because, of course, we have a lot of square meters there. So the same approach applies then to CO2 emissions. This is at the pixel level. Of course, one can zoom in quite into detail at the expense of accuracy, of course, because it's an archetype approach. Now we come to the results in terms of the static approach. So this means that we are not yet accounting for area which is available over time. So we are taking the total area, the total floor area, and assume it can be retrofitted overnight. And if we do so, and we calculate we determine this energy efficiency cost curve, we see that the full approach, as expected, is rather expensive. So we have positive cost. We have only a small bit where we have negative cost. The improvement approach is the most attractive, with quite a bit of measures with negative cost. And then it becomes only positive, whereas the intrinsic approach is somewhere in between. So this is in a way what one can expect if one thinks about how the cost has been calculated. And the same results are again shown here. So let's say the cost of delivered energy or of savings actually, then you would have here more red colors for full compared to the intrinsic approach, and the cheapest would be the improvement approach. But as I said, this is like assuming that all the building elements could be renovated overnight without considering any constraints. So we do need to consider those constraints. And some of those constraints are that we consider in our cost assessment. I've already mentioned that the refurbishment, so that means after a certain time, the heating needs to be replaced, the facade needs to be painted, so the non-energy measures, and that comes along with cost. But we also need to consider the available floor area. So we will have the total floor area. We are looking at the historical building stock. We are not including here the new buildings. We are retrofitting only the old ones. It gradually decreases. And we say that we will be demolishing at the end of the life these buildings, but we also consider the fact that it probably doesn't make so much sense to do a deep energy retrofit if we are closer to the end of life, to the demolition, than 30 years. So these are these darker gray areas. So the building would be lasting down here, this green, until, let's say, 2090, but we would only consider retrofitting until 2060. So this would be done. For multifamily, for single family, and for all the archetypes one by one. Now here come the results, and admittedly they are a little complicated to understand in first instance. So I hope I'll do a decent job. We distinguish here again the different cost assessment methods, okay? So these are now dynamic results. Dynamic results means that we consider that from one decade to the other, the amount of available floor area for retrofitting is limited, depending on the archetype. And we indeed also account for the fact that we don't retrofit if we are closer than 30 years to the end of life. And also we consider that we have a limited retrofit capacity. So here in this study, we set the maximum to 2% for the entire country. 2% per year can be retrofitted and not more. And then you get to a quite different results than we saw before. So let me first say, and we're not going to discuss that in detail, that the gray shades behind, that's a more static approach, whereas what we will be focusing on are the colored lines, the dashed colored lines. The black one is the reference, and it's decreasing because the total building stock is decreasing because we have this demolishing of very old buildings. So anyway, the energy use is decreasing even if we don't do retrofitting. So that's the reference. Then we have the blue one, which represents the technical potential, and that would be the maximum we could do. However, in the context of energy efficiency first, we are more interested in the economic potential, and that would be the yellow curve. So here we are now interested in looking at the differences in the decrease of here final energy. We do the same for greenhouse gas emissions and primary energy, in the difference depending on the cost assessment method. And I think we see something unexpected, because contrary to the static approach, we see that actually this intrinsic approach in this dynamic modeling, it allows to reduce the final energy demand more than the improvement approach and the full approach. You see the endpoint here is at 40, here we are below 40, and here we are again at 40. So why is that? What do the different approaches kind of struggle against? Well, the full approach is struggling against the fact that the costs are high. So you would, from a technical point of view, you could go much lower, but since the costs are so high and we want cost effectiveness as much as possible, we don't get below 40. The improvement approach struggles not so much against the cost, because we do it at the end of lifetime, we have to deduct the anyway cost, but against the fact that the available possibilities to retrofit are limited, because we have to wait all the time until the end of the life of the individual building element has been reached. Whereas this is not the case for the intrinsic approach. So essentially this difference comes from the fact that we can do early retrofit. And what is also interesting is in the previous curve, the energy efficiency cost curve, I showed you very, very big differences between the three approaches. Full approach was essentially economically not at all viable, and improvement was very interesting. Whereas here we see the differences for the yellow trajectory are rather limited because we are more realistic in our modeling approach by accounting for all these constraints. So I'll not go through greenhouse gas emissions and primary and just show you the type of graphs which Kai has prepared. So we have optimization in the one case for cost minimization, and in the other case for greenhouse gas emission reduction. So this would be kind of a technical minimum, and this would be the economic optimization. And we see, for example, for economic optimization, that a lot of activity in relative terms take place in 2030. There's much more red here, right? So in the first, at the beginning of the second decade, let's say, whereas for the greenhouse gas objective, it's more distributed. However, this is a bit deceiving because we don't see the total level of retrofitting because the floor area is not visible here, right? So what I will show you later is you could get the impression that there's more activity going on here than here, but this is not the case, as we'll see later on. So in other words, for greenhouse, if we want to minimize greenhouse gas emissions, we need to have much more retrofit activity as we would expect compared to the cost minimal. I said earlier on that the constraint we have is that the retrofit would not exceed 2% per year. Here you see that in some areas it's much more, but when I was referring to the 2%, I was meaning the total of the entire country for a given year. So on average, that constraint would be respected. Other interesting results from this analysis are that in spite of global warming, and we did different types of scenarios with different radiative forcing, the measures still remain interesting. So even if we go for sorry, I was jumping here, even if we go for very strong climate change, and the switch from old to the new warmer climate, it reduces the energy use and the CO2 emissions only by 25%. So that will by far not be enough. We do need to go for retrofit, as we know. And here you see, I think, very relevant numbers that if we, of course, this is an optimizer, so it does the right thing at the right moment for the right element in the right spot all the time. But if we do that, then we can reach a technical greenhouse gas emission reduction of 90% at a significant cost, but not unaffordable, 180 francs per ton CO2, so a bit less than 180 euros. And what is very interesting is that the cost optimal greenhouse gas reduction abatement is not so much lower. So a bit less than 80% at a negative cost. So this is even cost effective. Yeah. So this shows actually that by early retrofitting, you can actually come up with even a package of measures which is cost effective. And this is another, and soon I'll end with these very complicated graphs. This is the last one, but I think this shows the full power of the approach. For example, so again, we have the cost minimization on the left, we have the greenhouse gas reduction on the right. The total bars, they show the total potential. So for example, this is the total potential. Together it's 100%, and the colored bar sections represent what is actually done. So you see that down here, the colored bars are about maybe 60%, in the case of cost optimal, whereas it's 100% or it's it's 80%, 75% plus a bit for greenhouse gas optimal. So there's more activity if we minimize the emissions compared to the cost optimal, but it's also not a very big difference. Yeah, so let's say a bit more than 60 versus a bit more than 80. And you can also see in this approach what needs to be done when. So for example, in the greenhouse gas optimal case, you would do the retrofit. These are of course small numbers now here, but you would do quite a bit already in 2020 for these different archetypes, age classes, whereas you would wait a little bit if you go for cost optimal. So it tells you indeed what type of measure to do when and where. Also in terms of rural, for example, you can see that oil boilers, not amazingly, they are completely replaced in the case of greenhouse gas optimal, as opposed to cost optimal, where not the full potential is exploited. And I think what is also very interesting, and here I come back to one of the first slides, very important is if you look at the retrofit packages, what is really dominating in both cases is the passive house. So this system P, even in the cost optimal case, by far most measures are related to an entire retrofit implying passive house standard, followed by heat pumps only. So this is something I didn't show you in the beginning, but we also considered that. Heat pumps only come in very strongly in the cost optimal case, so that without doing the envelope, right? They don't at all come in if we go for the greenhouse gas optimal. There we would always do it together with the envelope. However, the envelope alone doesn't show up at all. I'm sorry. The envelope alone, without improving the heating system, doesn't occur in either of the two approaches. So this is the type of results we get, and I'm coming to the conclusions. Sorry, I took a little longer. So the key messages in methodological terms are that we really need to be careful with the cost assessment methods, because they very strongly determine the results, especially if we go for a static approach. We think that there is strong arguments to go for this intrinsic value approach for the reasons I gave, and the differences across these different approaches, they actually become less if we go for a dynamic modeling with these pathway approaches, where we account for all the constraints. So it really is important to do so for this type of analysis, and to ideally do indeed both, to combine indeed these different cost effectiveness approaches with the pathway analysis. We think that optimization models are the right way to represent the energy efficiency first ambition and objectives, to understand where the potentials are for the reasons I've mentioned a few times. So if we come back to this quote, we have just thinking back what we have done, we have very much used the optimization models for cost minimization from the private perspective, from the owner perspective, say from the microeconomic perspective. We could do it differently. We could address also external costs. We could address macroeconomic aspects, which I'll briefly touch upon in the coming slide. So just in a nutshell, a summary of the empirical results: greenhouse gas reduction, economically viable, so according to the energy efficiency first approach, of around 2/3 is possible until 2060. It includes, and that's the key thing, it includes energy early retrofit, That does not mean that everything is done before the end of life. It's selected measures which are done early, and in any case, heat pumps become extremely important. So I've mentioned this is a no regret measure, the heat pumps in spite of global warming. And in terms of limitations of the analysis, something Kai has spent a lot of time on, but which is admittedly a tricky area, right? There are, of course, uncertainties related to investment, related to future energy prices, CO2, and they do have, of course, a significant impact on the result. We also did not consider external costs. Well, we did by accounting for the current CO2 levy of 96 francs per ton CO2 in Switzerland, but no other external effects. I mean, one could do the same type of thing for health impact related to particulate matter, etc. And also, I think further work would be required in order to think more carefully about the obstacles. I mean, indeed, the real transition will be much slower because owners need to decide, they take their time, not everything can be done at the right moment. So in order to at least not be too far away from these pathways, quite ambitious measures, policy measures would need to be put into place. That needs to be studied separately. So in a nutshell, I think this work nicely shows that energy retrofit is not only technically feasible, but it can be economically viable, and it often is, even for deep energy retrofit, which is very demanding if we come to the economic assessment. The requirement of economic viability, and we do need further policy measures in actually to exploit this potential. So with this, I'm at the end, and I would like to refer to the most important documents prepared by Kai Streicher, and I'm very happy to take any questions and shall look into the Q&A and listen to Didier.